The SRAM, a short-range attack missile that has its own self-contained guidance system, is a strategic weapon which can carry a nuclear warhead. The SRAM can travel at supersonic speeds and will be able to penetrate sophisticated enemy defenses after being launched from carrier aircraft like the FB-111 or the B-52. Designed and developed for the Aeronautical Systems Division, the short-range attack air-to-ground missile has been undergoing many research and development performance tests at the White Sands Missile Range, New Mexico. The SRAM test program differs from those involving earlier missiles because of the extreme mission flexibility designed into the weapon. Each flight test is conducted under a different set of parameters, such as different launch positions on the test aircraft, different interpulse coast periods, and different altitudes. The performance tests include evaluating the missile trajectory, maneuverability, speed, and range. With a nuclear warhead, SRAM's range will permit it to be launched at a distance from the target and allow the releasing aircraft to escape from ground defense action. The versatility of the SRAM is demonstrated in this test, in which the missile is launched toward a target to the rear of the launch aircraft. SRAM's flight includes a 180-degree reversal of direction in its track to the target behind the FB-111. The supersonic nuclear-capable SRAM, when fully operational, is expected to add a powerful punch to the arsenal of weapons available to the FB-111 and late-model B-52s.
In a remote area of the Nevada desert, 65 miles northwest of Las Vegas, is the Department of Energy's Nevada test site. Occupying an area of about 1,300 square miles, the Nevada test site is slightly larger than the state of Rhode Island and is surrounded on 3 sides by the Nellis Air Force Base bombing and gunnery range. The Nevada test site has been our nation's principal nuclear explosives testing area since it was established in 1950. Since August 1962, all United States nuclear tests have been conducted underground. Most underground nuclear explosive experiments at the Nevada test site are conducted in large diameter drilled vertical holes. Depending on the design size or yield of the explosion, a hole is drilled to a depth calculated to contain the explosive energy in the earth and to minimize the chance of venting or escape of radioactive debris. Specialized drilling equipment and techniques developed at the Nevada test site have made possible the drilling of holes more than a mile deep and up to 12 feet in diameter. For each test, miles of cable are strung for transmission of signals to nearby recording stations. When preparations are complete, the canister containing the nuclear explosive and instruments for determining results of the test is lowered into the hole. After the nuclear explosive is in place, the shaft is filled with sand, gravel, and plugs of special plastic. These activities have been coordinated closely with simultaneous test preparations in the recording stations and at the control point, the nerve center and command headquarters for testing activities. Extensive precautions are taken to ensure the safety of both on-site workers and the inhabitants of nearby areas. A detailed study of weather and public safety considerations is made by a panel of experts. While each test is designed to be completely contained underground, all of the safety decisions are based on the worst accident that might conceivably occur. If a leak from the test might result in unacceptable levels of radiation at populated places, the test is postponed. The test location is deserted. All personnel have been evacuated from the forward areas of the test site, and the final party to leave the area arms the device to make it capable of producing a nuclear explosion. Special safety procedures ensure that the device cannot be detonated until it is armed, and the necessary coded signals are received from the control point. Members of the test staff are at their stations in the command room. Many of the men are veterans of more than 400 underground tests conducted from this building.
5, 4, 3, 2, 1, 0 time.
There is little to be seen at ground zero during a detonation. The Earth jumps a little and dust clouds rise. Deep underground, billions of atoms have released tremendous energy through fission or fusion. The materials in the device and the Earth around it are vaporized. In less than a millionth of a second, the all-important electrical signals which will indicate to scientists the results of this test are transmitted to recording devices above ground. Below, the explosive energy compacts the Earth to form a large spherical cavity. Radioactive products are captured in a layer of molten material which forms around the cavity. As the cavity cools, the molten material falls to the floor and solidifies into a puddle containing most of the radioactive products from the detonation. Valuable data on performance of the test explosive will be provided when samples of this material are recovered within a few days of the detonation. As the cavity cools further, pressure decreases. Earth and loose rocks fall from above into the void. Ordinarily, the chimneying continues until the Earth at the surface sinks and a saucer-like subsidence is formed, usually within a few minutes, but sometimes not for as long as hours, days, or even months. Underground testing of nuclear devices provides scientific information that cannot be gathered in any other way. The continuing weapons testing program at the Nevada test site is vital to our nation's security.
On the morning of January 17, 1966, a B-52 aircraft carrying nuclear weapons collided with a tanker aircraft during routine refueling operations. The collision broke loose 4 nuclear weapons. The high explosive in 2 of the weapons detonated upon ground impact, scattering plutonium over a wide agricultural area. The accident occurred in the vicinity of Palomares on the southeast coast of Spain. Although the detonation of the high explosive caused no loss of human life, the cost of cleanup operations has run well over $50 million, and monitoring of the area's populace, soil, and farm products continues to this day. This accident, and the possibility of others, increased the emphasis at the Los Alamos Scientific Laboratory to develop an insensitive high explosive to enhance nuclear weapons safety. This Los Alamos developed insensitive high explosive, PBX 9502, consists of 95% triamino trinitrobenzene and 5% Kel F800, a plastic binder. PBX 9502 is formed into the desired shape by molding and machining in the same manner as PBX 9404, the explosive commonly used in nuclear weapons. In a series of tests conducted by the Los Alamos Scientific Laboratory and Sandia Laboratories, Albuquerque, these 2 high explosives were subjected to intense thermal and high-impact environments. In the first test, samples of insensitive high explosive and PBX 9404 were each confined in heavy steel pressure vessels. Each assembly was wrapped with electrical heat tape, surrounded by insulation, and heated at a rate of 122 degrees Fahrenheit per hour. At 570 degrees, thermal decomposition of the insensitive high explosive caused a pressure buildup that broke the container lid, but detonation did not occur. In the experiments with the PBX 9404, detonation occurred at 290 degrees, entirely destroying the pressure vessel and its container. Large-scale model impact tests using identical quantities of high explosive were performed on a pull-down facility. The target consisted of layers of steel and reinforced concrete. In this first test, a model laydown bomb containing insensitive high explosive strikes the target at 850 feet per second. The insensitive high explosive does not detonate. Here, a model containing PBX 9404 strikes the target at 440 feet per second. The high explosive detonates. These tests were followed by impact tests of bomb mock-ups on a sled track. Test conditions for the test units were identical. The target for these tests consisted of reinforced concrete backed up by sand and a steel containment box. Here we see a test unit containing insensitive high explosive accelerate to 500 feet per second and strike the target without detonation. In this test, a unit containing PBX 9404 is also accelerated to 500 feet per second. It strikes the target and detonates. In a split-screen close-up of these tests, the insensitive high explosive unit is on the left half of your screen, and the PBX 9404 unit is on the right. The PBX 9404 explosion is very similar to that which contaminated almost 400 acres of land in the Palomares incident. Had insensitive high explosive been available at the time, contamination would have been a small fraction of what it actually was. Since the insensitive high explosive would not have detonated, the cleanup problems would have been much less complex. In fact, the fragments of the weapons would have been recoverable at the impact site, as these fragments were recovered after a severe impact test of the insensitive high explosive PBX 9502. How do we detonate insensitive high explosive? In this test, we intentionally detonate an insensitive high explosive system. The detonation was initiated by the 1E34 detonator. This detonator was developed by Los Alamos especially for insensitive high explosive, and tests have shown that the new detonator system is safe, reliable, and effective. Recent versions of the B-61 bomb incorporate both the insensitive high explosive and the 1E34 detonator. The use of insensitive high explosive has significantly increased high explosive safety in the manufacture and transport of nuclear weapons, as well as in all related military operations. Insensitive high explosive has also provided an important additional safety factor in such eventualities as accidental airdrops, plane crashes, and fires. The development and evaluation of the insensitive high explosive PBX 9502 is part of the continuing joint effort by Sandia Laboratories and the Los Alamos Scientific Laboratory to provide enhanced high explosive safety for nuclear weapons. In 1954, for the first time on national television, the American public witnessed the awesome power of a new weapon, a thermonuclear bomb. This film is a capsulation of that broadcast, showing actual footage of the event Operation Ivy, marking America's transition from atom bomb to H-bomb, a transition from yields in the kiloton range to the megaton range, 1,000 times more powerful. On November 17, 1952, the Mike device, first thermonuclear assembly, was tested at Eniwetok Atoll in the Pacific Proving Grounds by Joint Task Force 132 in Operation Ivy.
I've been a member of firing parties before, but this was different somehow. A man standing, as I stood, on the outside of the building housing the Mike device couldn't help but feel, to sense the importance of this moment. Inside, a handful of men were making a final check. We're arming a device which could be the key to a new era in atomic weaponeering. I don't know just how the others felt, but I felt small when I thought of the experiment being readied inside. This one test could take us out of the realm of kilotons into the fantastic world of megatons.
The test islands for Mike are located at the top, or the northern sector, of Eniwetok Atoll, some 25 miles from Perry and Eniwetok, the two base islands of this atoll proving grounds. There are three main islands making up the test site. These are Alugilab, Teeter, and Bogan. Early in the game, these islands were linked together by causeways.
Okay, Teacher, you take this one.
What do you feel are the unusual aspects of your operation?
Well, we like to believe that Ivy is a milestone in atomic development. I believe that in many ways Ivy is another Trinity, the beginning of something, and we hope the beginning of the H-bomb era.
5, 4, 3, 2, 1, T0.
The cloud is still rising. 70,000 feet now, if the last estimate I heard is true.
An island completely erased. Mike was power, the kind of titanic energy released by stars. But even the largest man-made explosion in the history of the world has little meaning unless we compare it to everyday items we understand. So at this point, let's replay the detonation. Go back and watch Mike in action once again. Remember those final last seconds?
5, 4, 3, 2, 1, T0.
This is the largest fireball ever produced. At its maximum, it measures about 3 1/4 miles in diameter. Compared to the skyline of New York, this means that with the Empire State Building as 0 point, the Mike fireball would extend downtown to Washington Square and uptown to Central Park. In other words, the fireball alone would engulf about 1/4 of the island of Manhattan. The tremendous upsurge of air from the detonation rapidly pushes up the Mike cloud. Again, nothing of this height and width has ever before been witnessed. If the picture is stopped at this point in the cloud's growth, the height of the cloud is approximately 40,000 feet. This means that 32 Empire State Buildings at 1,250 feet per building could be piled one on top the other before they would attain the cloud's height at this time, roughly 2 minutes after 0. Some 10 minutes later, the cloud approaches its maximum. At this time, the mushroom portion of the cloud has pushed up to around 10 miles and spreads out along the base of the stratosphere to a width of about 100 miles, while the stem itself is pushed upward deep into the stratosphere to a height of about 25 miles. The results of this tremendous power can be shown at the atoll. Here is an aerial photo of the test area of the atoll before the blast. And here is the same area after the blast, showing the crater caused by Mike. The outlined island in the center is former Alugilab, the 0 island. Sections of the islands on either side have been chopped off. The crater is roughly a mile in diameter. When it is illustrated that some 14 Pentagon buildings could be comfortably accommodated in this hole, the size of the Mike crater becomes more real. In profile, the crater gradually slopes down to a maximum depth of some 175 feet. or equivalent to the height of a 17-story building. The lateral destructive effects are the greatest yet observed from a single explosive device. Without getting into the areas of target evaluation or secondary effects, it can be safely assumed that there was complete annihilation within a radius of 3 miles, or out to and including all of Engiby, that there was severe to moderate damage out to 7 miles or down to Ruggiero, and that light damage extended as far as 10 miles or down to Runnet. Relating this area of damage to a city like Washington, D.C. would present a picture something like this. With the capital as 0 point, there would be complete annihilation west to Arlington Cemetery, east to the Anacostia River, north to the Soldiers' Home, and south to Bowling Field. Complete annihilation, and that is mentioning merely the primary damage.
Thus, the United States entered the thermonuclear age in 1952, soon to be joined by other nations. Here in the National Atomic Museum, you can see a Mark 17 bomb case. The Mark 17 was the first droppable thermonuclear bomb, and examples of technological advances that followed.